So, welcome to the next session. Now, we are going to discuss about the plasma sources. So, why do we need plasma? Because plasma is the only source where we can generate very high temperatures without endangering our cells. Okay. So, high temperature plasmas generated from electrical power sources where collisions are introduced by electrical currents. Collisions of the atoms and ions are induced by electrical currents. That means, I think most of you already know by now that every electric current is associated with a little bit of magnetic current also. So, positive ions, negative ions, all those things will be there, and the high electrical power sources generally induce electrical currents that are useful for the analysis of solids, liquids, gases, etc., etc. So, there are different ways of introducing the plasma. They are known as direct current plasma. I just take DC. You know what is DC? What is AC? AC is where the current goes and then stops and then again starts. 0 plus 1, 0 plus 1, 0 plus direct plasma, it is a continuous signal. And then inductively coupled plasma, this we will discuss a little bit more, and then microwave induced plasma. We know 3 types of generating plasma. In all these plasmas, high temperatures are generated. So, a DC plasma source consists of a DC arc discharge. This we have already discussed earlier today. And the discharge between 2 electrodes is carried out using argon in between gas. So, the gas is introduced in a tangential flow. That means, if the electrodes are coming like this, argon is introduced like this in between. Electrodes are like this, argon is tangential to that. So, the resultant gas, it is not moving freely, it is constricted because it is just touching and going. If you know what is a tangent, if you take a curve, something just touches and goes is a tangent, a straight line, a curve like this, a line touching that. So, I am introducing argon in a touching way and the resultant gas is constricted, that results in increased current density and higher temperature. The DC plasma is operated using 5 to 30 amperes. So, how much amperes you get in your normal day to day houses? What is the amperage? At home, we get 5 amps. Electric plugs, they are 5 amps and 15 amps. Okay, maximum allowed inside the homes is 5 to 15. If you use an electric heater for a bath, etc., for a fridge, you get 15 amps plug, otherwise 5 amps plug for normal lighting. So, DC plasma is generated using 5 to 30 angstroms, that is slightly double than what we normally get at home. That means, it can be done in a laboratory, simple. Okay. So, the gas flow rates, gas should be passing through the electrode in a tangential way. So, the gas must be flowing, it must have a, how do you define a flowing gas? Speed. So, the speed is up to 70 liters per minute is the gas required, it is very high. Okay. So, the plasma temperatures ranges 4700 to 11,000 degree Kelvin. If you have 30 angstroms electric current I pass gas tangentially, 11,000 degree Kelvin temperature is generated. What is the sun's temperature on the outside? The temperature of the sun at the outer edge is around 6,000 degrees. What you see in the morning, if you look at the sun, there will be red diffuse light around the sun, that is corona. Okay, that corona temperature is around 6,000 Kelvin, and here how much you are generating at home in the laboratory? 11,000, double than that temperature, using only 30 amps electric current. That means it can be very easily generated at home in a small space. Okay, that is the beauty of ICP. Now, I also want to analyze my sample. So, the sample also must be introduced into the plasma, that also should come via a tangential flow, correct. So, the sample is introduced as an aerosol. I can't introduce a solid sample flowing through. I need a liquid, and that liquid should be in the form of very fine droplets like an aerosol. You know what is an aerosol? Room freshener. Just think of a room freshener. If you press the button, psst, like that, small, very small droplets come out. Any window cleaner you take, press that button, it will give a fine mist. So, that mist contains very small droplets and they will be flowing, they will be moving. So, that is the produced by that button with a small hole is known as nebulizer. So, the job of nebulizer is to convert a given liquid into a small droplet, and that is positioned between the electrodes. In between the electrodes, the gas is flowing and sample is introduced in the form of a vapor. Okay. That means, the electrodes are anodes and cathodes, and gas is there, that is argon, and then sample is there in the form of vapor or aerosol containing liquid, very small droplets. It will be like a mist or a fog, very simple definition. So, the optical measurement region is located across the base of the confluence. Two electrodes are there, gas is there. So, I need a detector and radiation source, both of them on the other each side. So, it is located near the base of the confluence to eliminate high background from the arc plasma. Arc itself gives you lot of radiation. Now, I want to introduce a sample, I want to measure a small concentration of the analyte. Now, the background itself is so high, so I have to eliminate as much background as possible, so that the small difference from the sample is highlighted prominently. So, it is that is the technique of high temperature plasma analysis. So, one is to strike the plasma, another is to remove the extra unwanted radiations coming from the plasma. If they come from the sample, we are happy, because that is what we are going to measure, right. So, the analysis using inductive coupled plasma ICP AES is useful for about samples containing 45% of the dissolved solids. 45% is quite high if you are not aware of the requirement of chemical analysis. Normally 5% solids is like milk. Okay, 5 to 10% is milk, 35% is curds or something like that, and 45% can be your sample in ICP AES. You can make a big thick slurry and still introduce. That is the beauty of ICP analysis. In atomic absorption or in spectrometry, we do not want the solutions to be turbid at all, right. We want them to be very clear colored solutions. In atomic absorption, I can't use turbid solutions because it clogs the burner, then the sample can't come, can't burn. But in ICP, I can make a slurry and still introduce as a fine spray. Okay. So, the advantage is a low cost DC power supply can be used for continuous operation, and unfortunately, that is not possible because the electrodes continuously erode. If you take two electrodes, you bring them nearer and nearer, a arc will strike. Okay. So, after some time what happens? During the arc, after some time during the arc, the material will burn. So, the gap will increase. So, the arc will become less intense. So, DC arc is not really suitable because you do not know when the arc will go off. Only when they are very near, voltage is very high, arc is struck. So, as the material burns, signal will fall down. So, arc may go off, then you do not have a excitation source at all. So, what people do is, as the arc, as the sample burns, there is another servo system that keeps on pushing it nearer and nearer. As it burns, it pushes nearer. So, distance between the two electrodes must be maintained constant. It is done by computer also. Okay. So, still the problem is continuous operation using DC arc is slightly difficult. So, because the electrodes continuously erode. In this context, we want electrodeless plasma. You generate a plasma without electrodes, then where is the question of burning electrodes? It is not there, right. So, that is inductively coupled plasma that is used for atomic emission spectrometry. Okay. So, how do we do that? Is very simple. I am showing you a picture of the plasma torch. So, what happens here? I have a liquid sample. Imagine your choline bottle at home with a tube inside, okay, and then you are spraying on the glass. Okay. So, the sample, look at the figure here, there is a small capillary, the sample is coming out like this. Okay. It is shaded portion, and outside there is a shell here, one on the top, one at the bottom. So, here what I am putting? Gas. You see my arrow? My gas is coming, one through this below bottom and another through the top. Okay. That means, the capillary with which through which sample is coming, it is put in a tube, that tube has argon gas passing through. So, all of them will open up together near the edge. This is known as nozzle. Okay. So, this distance has been very much standardized using lot of research methodologies. One is the distance between this point and the nozzle is approximately 40 millimeter, and this distance between the sample input, this could be your conical flask, this end, a small tube dipping in a conical flask. From this point to the gas nozzle is 25 mm. So, 40 mm is 4 centimeter. This is 2.5 centimeter. Total length is about 6.5 centimeter, that is all. And this is known as plasma torch. I press the sample, it comes out, I pass the gas. So, everything will pull towards the nozzle. Okay. So, that is how I am producing the plasma. Now, how does a plasma is generated? Just because I pass the gas and I pass the sample does not mean plasma is generated. You need to strike an arc. Now, the inductively coupled plasma is like electricity generated in a normal place where a hydroelectric power or coal electric power is generated, thermal power stations. What do? They take coal, burn it to produce steam. Okay. The steam is passed through a coil, and that coil is it is analogous to a transformer, which is primary one winding in one winding, this winding tube will pass through, go out, in and out, in and out, in and out. That is how a transformer works. It is known as dynamo. If you freshen up your 9th standard physics, a transformer how it works, a dynamo how it works is taught in your science books. So, you just look it up, but essentially right now it is enough if I tell you that there is a primary coil which is magnetized, I pass electric current, and another coil is there, and this coil goes in and out. So, this movement generates electricity. Okay. That is how we are doing it. So, one is known as the load coil. The thicker the load, the more electricity is generated. Another is known as the inductively coupled current coil. One is load coil, another is current coil. So, the current coil keeps on going inside and outside, and the electricity is generated. So, in inductively coupled plasma, we use electric currents, and that is known as oscillatory current, because it keeps on oscillating between 0 and 1 the AC, and but it is from a radio frequency generator. What is a radio frequency generator? It is again a coil through which something moves in and out, and nowadays radio frequency generators or radio frequency monitors are used in all hotels to open your lock. Okay. You just insert a radio frequency card and it opens the lock. They are very easily available for about 100 rupees, 3 or 200 rupees, 300 rupees, something like that. So, here what is important for us to understand is, I need to make a transformer. One is through RF coil, okay. One goes through inside and outside, another is load coil. Load coil is through AC. Okay. So, the ionized argon gas, I am passing argon gas. So, this argon gas is coupled inductively to the radio frequency source. That means, the argon gas is connected to radio frequency source, it comes through that. Okay. So, the plasma torch, what I had discussed earlier, it consists of two concentric tubes, tube inside a tube. So, that is how inside the sample, outside in another tube, two gases are coming. So, there argon gas is flowing, that is tangentially to the between the inner and outer tubes to provide cooling, because when the temperature is raised, how much? 11,000 degree Kelvin. So, 11,000 degree Kelvin, many things will melt. We do not want things to melt, is not it? So, I have to cool it. So, argon gas also cools because fresh argon keeps on coming. So, it keeps the temperature cooler. So, in between the inner and outer tubes, it provides cooling also, it generates plasma, it generates high temperature, at the same time it prevents melting. So, argon gas flowing through the smaller tube interacts with the magnetic field, that is the mechanism, to generate sufficient external energy to ionize the gas. That is how plasma is generated. Plasma is generated from the gas ions. Okay. Some gas is ionized, remaining extra gas is used for cooling and generating this thing. Beautiful arrangement. So, initial ionization can be provided by a Tesla discharge, magnetic discharge, and the plasma is sustained by ionized argon. Once argon keeps on flowing, plasma will be keep on generating. Only thing is there are no two electrodes here which will erode. So, I have a continuous supply of high temperature zone in which argon ions are there and high temperature is provided in a small zone, just like a flame. If you remember a candle flame will be like this and candle flame will be like this, is not it? So, this candle flame, you can imagine if I use argon plasma, it will be a very small 1 centimeter size, where 11,000 degree temperature will be maintained. That is how the plasma is sustained by ionized argon, and that is formed in high temperature plasma. So, in that we are passing our sample through the capillary. I had shown you the figure just now. If you do not remember, this is the one, this is the capillary. So, the argon that is passing through, it provides a cooling atmosphere, it provides a plasma in front of this nozzle about 1 centimeter length. Here you can see I am pointing out 1 centimeter size, and that also generates high temperature. Okay. So, in that I am directing the sample through a capillary tube and RF generator. These are technical details. 1:5 kilowatt and 3 to 100 megahertz is the RF generator. These things are available commercially. If you go to Bangalore, SP Road, any electronic shop will provide you an RF generator for about 2,500 rupees. Okay. So, why I am telling you this is you can make an ICP AES in your home, in your laboratory using known things. A quartz prism is available, RF generator is available, argon gas is available. Okay. So, many that is the one of the reasons why I keep on teaching about the instrumentations in so much detail. You can make, I can make you a businessman out of you if you have got interest in making things. Things are no rocket science. Okay. So, you need 3 to 100 megahertz to sustain the argon plasma that produces 5 to 10,000 degree Kelvin, depending upon the input power. What is the power? 5 to 30 amperes, and then gas flow rate about 70 liters per minute, and composition very well known, argon gas 99.99% pure, organic is sufficient, and it has to be coupled to the RF gas generator. If you start using passing argon and start working, it is coupled already. There is nothing very special about it. So, optimum weaving heights vary with the analyte which is about 3 to 10 mm range in multi-element analysis. You remember the nozzle? So, in front of the nozzle there is a plasma range, that is 3 to 10 millimeter distance plasma. In that plasma you can do multi-element analysis if your sample comes through as a aerosol. So, ICP is an extremely versatile source for atomic emission spectroscopy. Sample solutions are nebulized into a chamber, that is the 1 centimeter zone I had shown you, and the aerosol is directed into the plasma using a carrier gas, that is argon, same argon from the same source. Okay. So, then what you should do? Measure the emission and then standard calibration curves for most of the elements are linear over 1 ppm, 10 ppm, 100 ppm, 1000 ppm, 10,000 ppm, 6 orders of magnitude in concentration, and detection limits are 0.1 ppb. Parts per billion is how much? 10 raised to minus 9. Okay. 0.1 ppb, 1 ppb is 10 raised to minus 9 gram, 0.1 is 10 raised to minus 10 grams, correct. Quantitatively, that is the minimum you can determine. Now, suppose I want you to determine aluminum in the brain. You know, most of you must be aware that Alzheimer's disease is related to aluminum, isn't it? You keep on drinking Coca-Cola containing an aluminum can, several thousands if you drink, there will be enough aluminum to give you Alzheimer's disease before you cross 50 years of age. So, but that aluminum has to go into the brain. Now, how will you analyze aluminum in the brain? It has to be in, you can't take full brain and dissolve it and do the analysis, right. You have to take a small portion of the brain, already it is in ppm, and you take only 0.1 gram or 0.2 gram of the brain, in that 10 raised to minus 10 grams. So, the actual detection limit would be 10 raised to minus 14 or minus 15 grams, because you can't take 10 gram of the brain for analysis, you have to take very small quantity, in that 10 raised to minus 1. So, that is how the demand for chemical analysis in parts per million and parts per billion level is important, and that is how we get the lowest detection limits. The push is for lowest detection limit for the chemical analysis. Now, you can imagine even some of the atmospheric gases, right. There is nickel in the air, arsenic in the air, lead in the air. Well, so many petrol vehicles, etc., they used to contain lead. Nowadays, they do not contain lead, but lead is there in the air. Now, that lead is already in the ppm or parts per ppb level, parts per billion level. Imagine, but you can't take 100 liters of the gas sample, air sample and analyze. You will take only 5 ml or 10 ml. In that 0.1 ppb lead you have to analyze. So, the demand on the chemical analyst in parts per billion or parts per billion level, parts per trillion level, 10 raised to minus 12 level is so high that it is difficult to quantize and to rely on the analysis, because we take very small sample. The demands on the analyst are so severe, you can imagine. Suppose there is a patient with spinal cord problem, and then you can't take 5 ml, 10 ml of the spinal fluid, isn't it. So, again you are restricted to few microliters of the sample, again analyze. That is how the demand keeps on increasing. So, the limits of detection range in ICP from 0.1 to 200 parts per billion. Okay. Now, I have discussed about the inductively coupled plasma. Now, we will discuss a little about microwave induced plasma, but it is not very important because ICP, inductive coupled plasma, has become more popular, and this plasma source consists of a microwave resonator or a cavity inductively coupled to high frequency generator by means of a coaxial waveguide. You know the optical fibers, they are known as coaxial waveguide. So, microwave induced plasma also provides fairly good temperature, but it uses 200 to 500 watt of power at a frequency of 2 to 45 gigahertz. So, the power is transferred to the microwave cavity by means of a coupling loop, and the optimum use for microwave induced plasma is for the analysis of gases, not metal ions. And so, the gases are carbon, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine and sulfur, etc. Not all of them, because mostly gases in the periodic table can be analyzed using microwave induced plasma. So, the detection limits again are 1 to 50 ppb of the gas elements, and calibration curves are of the linear over 3 to 4 orders of the magnitude. So, now if I summarize our discussion about the inductive coupled plasma, I have taught you two sources. One is inductively coupled plasma that generates about 11,000 degree Kelvin using argon as a coolant gas, as an ionizing gas and as a plasma source, and another is the microwave induced plasma, which is using about 500 watt of power, but useful for the analysis of gases. So, in pollution monitoring, if you wish to measure, analyze gases, you should go for microwave induced plasma. If you wish to analyze for metals, go for ICP AES. Okay. So, how do we do? Assume that you know all about how to make a source microwave plasma. Now, you also know how to introduce the sample also through a plasma torch, correct. Now, what is the next step in the analysis? To separate the radiation coming from the excited atoms, metals, gases, etc., and that is part of spectroscopy. So, you need to put the radiation coming out from the plasma into some sort of a prism or a grating or some other optical arrangement which can separate different emission lines. Okay. And the arrangement of the prisms, mirrors, gratings and all those things constitute what is known as optical mountings in ICP. Optical mounting is nothing but a design where in a box the radiation passes from the source to the mirror to the concentrate to make the rays parallel, to take a small portion of the sample that comes out, separate them into different wavelengths and make a radiation, convert it into current, and that current should be converted back into the signal. So, optical mountings are very important in any spectroscopic instrument, and they are all mounted on a flat plate through which radiation will pass through until it reaches the detector. I may put a concave mirror, it produces parallel radiation. I may put a lens, it produces a radiation that focuses on the focal length. From the focal length, I want to put it on a prism or a grating to separate different lines, WIBGOR, rainbow, blue, yellow, red and all that. And then from there I have to choose which color. That depends upon the element which we want to analyze. So, those things are available in the database. So, once I have that, I have to organize that. So, the optical arrangement is known as optical bench. It has to be a very flat piece of glass or a metal on which different optical components are mounted. So, this is known as optical mounting. So, electromagnetic radiation can be in an optical mounting. Electromagnetic radiation can be separated into its components by, that is the function of optical mounting. So, by a variety of optical arrangements using gratings, prisms, slits, mirrors and all that. So, for high resolution spectroscopy, the incident radiation can be separated in two dimensional ways. One is electrical component, another is magnetic component. Okay. Any electromagnetic radiation, I have already taught you that it has got an electrical component and a magnetic component. So, in two dimensions they can be separated by using an Eschel grating and separating the multiple orders with a prism. So, Fourier transform spectroscopy also has been developed that extends the wavelength range to ultraviolet region. Okay. So, visible region and ultraviolet region, this is where most of the emission lines of all elements that are there in the periodic table will fall. So, we need the optics to cover ultraviolet and visible range. This we will see how, what are the best ways of mounting the optical arrangement in a inductively coupled plasma spectrometer in our next class. Thank you very much.